Good morning, good afternoon, and good evening. Thank you, everyone, for taking time out of your busy day to join us for a very special event. I'd now like to pass the floor to our presenter today, Robert Ferrulo, a senior technical marketing engineer with Mojo Network. Robert comes to us from Maru and Alcatel with over 20 years of experience in the networking industry and nearly a decade in Wi-Fi. Today, Robert will be addressing the challenge of providing reliable Wi-Fi access while also taking you through how Wave 2 technology can quadruple the capacity of your campus WLAN. And without any further ado, I'll go ahead and pass the floor to Robert.
Well, all right, Erica, thank you for that introduction and welcome all. We got a lot to get through today, so we'll get right into it. You see the agenda there on the screen. We'll first present the challenge, a challenge. There are many challenges, of course, with deploying a wireless LAN solution in a campus environment, but we'll stick to one related to really around capacity. We'll go through a simplified wireless LAN capacity planning session, and we'll also take a quick look at the C120, which is our latest Wave 2 AP platform. And then we'll go through some actual solutions for lecture hall. First, we'll start with an 11N. Not that you'll be doing 11N deployments. I think those days are over, but I'm sure there are still a number of lecture halls today throughout the US and globe where they have 11N solution installed. And we'll look at a Wave 1 solution, and then move on to a Wave 2 solution with multis and MIMO, and then follow up with some Q&A towards the end. All right, the challenge. Again, this is one challenge, but for me, it's one of the greatest challenges because if you look at Wi-Fi, and you have security challenges, of course, but most of the security challenges have been pretty well handled with WPA2 and with other types of with WIPs, certainly with our WIP solution and firewall solution and so on. But still, one of the biggest challenges is reliability. That is access. And what I like to say is that you want to be able to design a wireless LAN that will support all applications on all devices. I'm talking smartphones, tablets, and laptops here. Obviously, you're not going to, in a campus environment, you'll have devices like Xboxes and PS4s, so we're not talking about those. They need to work, but we're not talking about running all applications on those, obviously. And these devices that need to work anytime and anywhere. And that's a lot easier said than done, I'm sure most of you know, because the requirements are getting tougher. You have higher client densities, higher bit rate applications, a lot of latency sensitive applications, whether it's video conferencing or distance learning, and I'm not talking about on demand, but real time, and also with BYOD and university BYOD environments, you don't have control over the devices, the types of devices that people are going to be bringing in and expecting their applications to work all the time, anywhere. And so in the old days, you could say, well, before this device gets on a network, we're going to go through a proof of concept, or we're going to pilot it. We're going to pilot this build of driver, and we're going to make sure that this device will work all the time, anywhere. That's obviously not happening these days. So you're going to have a lot of variables there, things out of your control. Also, it's an unlicensed spectrum. And I was recently at the LTE conference where, the Wi-Fi Alliance, where we're looking at how to play nice with LTE, or how LTE is hopefully going to play nice with us, LTE unlicensed. All right, so we not just LTE, but there are all other types of devices that are already in our environment, like microwave ovens or non-Wi-Fi sources of interference that you have to deal with. So a lot of variables. And it's a shared medium, unlicensed spectrum, and so your wireless LAN system needs to be able to handle whatever type of dynamic changes it's faced with. So now moving on to simplified wireless LAN capacity. This is just one methodology we're going to go through, but first we'll take a look at use case discovery. I like to design around use cases. Of course, we can use Mojo Planner or other types of planners to do a predictive site survey. And they're good to get a rough estimate of what you may need for a floor or for a building. But really what it comes down to is, use cases, because most buildings or most floors of a university building, the use cases are not uniform throughout the whole building. You're going to have some areas where you may need higher density, higher throughput, aggregate throughput support compared to others. So really, I like to get down to the use case deployment methodology. And to do that, first of all, we're going to have to do a requirements discovery. Look at the types of clients, how many clients, whether they're single stream or two stream, 11AC, 11N, and look at the applications that they're going to be supporting there. And usually you want to discover the application that is the most demanding, because you want to design your network for the worst case scenario, so to speak. And you're looking for usage patterns. You're looking for what are the maximum number of devices we're going to have in a particular area at any one time. And we want to design not just for that current usage pattern, but projecting, in 2 years, 3 years, 5 years, however long you plan to use the wireless LAN that you're going to be installing, throughout the life cycle of the deployment. So you have to kind of project, forward, not just with usage pattern, but also application, knowing what's on the horizon in terms of application. Is 4K video being planned for? I mean, I know it sounds like, well, no, probably not. It's ridiculous. It's 25 megabits per second. But still, you have to, think in those terms. Also, the building, the type of material used, the type of attenuation, the size of the building, the RF environment. Whether it's wide open or if it's got a lot of attenuation and reflective material and so on. Also, spectrum availability. Do you have DFS channels available? If not, are all DFS channels unavailable, or is it just 1 or 2 DFS channels unavailable, and so on? So that way we can come up with a use case, which is the number of devices, types of devices, applications, usage patterns for a given area. And once we know that, then we can actually do some channel capacity planning. So just wanted to take a moment to talk about Wave 2 clients. They're here. First, if you see in the left-hand column or 2 columns, you'll see the 1x1 and 2x2. Those are single user Wave 1. And so a lot of those clients are, I'm sure, you're familiar with a lot of them. But on the right side, the right 2 columns, we have Wave 2 clients and 1x1 and 2x2. And I have some of these clients actually in my lab, and I'm using them to do multi-user MIMO efficacy testing. And so you can see, for instance, the HTC, the Aspire E-Series, there are a number of those that are 1x1, and so on. And Google Nexus 5, we have those in the lab. Those are 2x2. And we need those, obviously, because we're trying to, look at basically the benefits from multi-user MIMO. So we've been using some of those clients for that purpose. But they're there, they're available. You can start purchasing them now. In a campus environment, we probably don't have too much control over the types of clients that students are going to bring in. But they get refreshed pretty quickly. Certainly on the handset side, the turnover is pretty quick in terms of refresh. The laptop's probably a little bit longer. But we expect to see a lot of multi-user MIMO clients, and certainly within the next year or two, percentage is going to keep just going up there. Applications. So we need to know your application bit rates. Again, we got to design for the most challenging scenario or use case. And I put the video down there for like high definition video. We do see 720p video or high definition video running on campus networks and also in K-12 and other environments. And it can be anywhere from 3 to 5 megabits with H.264 encoding. Not sure with the new H.265 what that's going to turn out to be. But if you look at video streaming like 4K, now probably not going to run 4K to student devices, but maybe in the front of the room there's a projector or most likely a projector that will support 4K in the future, and that projector, if it's wireless, would need to have be able to support 18 to 25 megabits per second. So that's pretty demanding. I don't have the video gaming system here listed because I actually don't know. I've never done a sniff of that. I don't know. So for instance, in dormitories, I know that a lot of students are going to bring their PS4s or whatever, and you probably want to get a sniff of that or look at your management system, wireless LAN management system, to benchmark that throughput, so you can design for those type of systems. All right, spectrum availability. So here's one that should be not very, controversial, and it should, this by looking at this graph, we can or display the image here, we can see if we take a quick look at the spectrum availability. Let's look at the green and the blue or gray in the U.S. So we have, if we're looking at 80 megahertz channels, we have 1, 2, 3, 4, 5, 6, 80 megahertz channels. Now, I want to point that out. And by the way, this is the channels 120 through 24 and 128. Those channels are available again, and RAP do support those channels. And so that gives you 6 non-overlapping 80 megahertz channels. So when people try to say don't use 80 megahertz channels, as you see later on when we go through some of the exercises, you really do need 80 megahertz channels if you want to see the benefits of wave 1, because if you compare wave 11N, which supported 40 megahertz channels, 11N supported up to 40 megahertz channels, and wave 1 or wave 1 supports up to 80 megahertz channels, that's where you get your bang for your buck. I mean, yes, you get beam forming and some other features that are in like low density parity check for forward error correction, but you really get your big bang for your buck when you double the channel width. And so I totally am a proponent of using 80 megahertz channels when you have the spectrum available. 6 non-overlapping 80 megahertz channels is plenty to design a network around. Remember, we used to work with 3 with 1.6.11 in the 2.4. It wasn't ideal, but it was doable. Far from ideal, obviously. The pink, we have some additional spectrum that's been identified by the FCC. Which will be available in the future, more than likely. It's very highly likely that it's going to happen, but I don't really have the dates for that yet. Okay, and by the way, if you can't use the DFS channel, it's usually 1, maybe 2 DFS channels, most likely. It's not like you're in an area. Most people are not, in most environments are not in an area where no DFS channels are available. You would probably have to, basically remove a channel. If you're seeing a radar event on a channel, you would just remove that channel from your candidate list. That's something that our system supports, obviously, and most systems have that ability where you can just remove a DFS channel that's seeing radar events from the candidate list. All right, now I'm going to just go through some very basic data rate and versus estimated channel capacity for some 11AC environments. We'll start with the data rates because we got to use this as basically the starting point, because we're going to show some percentages of actual throughput based on density. And so we'll start with the data rate. And for 11AC max data rates, you see that, for instance, at 80 megahertz, a 1x1 client, one spatial stream client, it could connect at a max data rate of 433 megabits. And for a 2 spatial stream client, like a MacBook Air, can connect, of course, if it's near the AP, good signal strength using MCS rate 9, you can connect at 867. Those are data rates, obviously not throughput rates. Throughput rates, we're going to estimate that we're going to get for a single client up to 60% of max throughput rate, max data rate. So for TCP throughput, you can expect to get on a good client, on a good clean channel, whether it's for instance 80 megahertz channel for a 1x1 or 1 spatial stream client, like this. Let's see, I'm trying to think of a 1x1 client. Let's see, NHC 1 M8. You can connect and you would see approximately 260 megabits of throughput. Now I happen to have some 1+2s. And they are 1x1 clients. They happen to be multis and MIMO clients. But when we do a single client throughput test, we're not relying on multis and MIMO, and we're able to see up to 320 megabits per second. Now that's like a 70-something percent, 75% of PHY rate. Very unusual. Usually you only get up to about 60% of max data rate, maybe 65 on a really good client. But we start here because this is the baseline and used as a reference. It thinks, in general, with a single user MIMO, it doesn't get better than this. As we add more clients, the aggregate throughput for those clients that we're connecting to the to the access point is going to go down because of contention loss, mainly due to contention loss. For instance, if we go up to say 2 to 15 clients, but closer to 15 clients here, and we do a throughput test to those same 15 one-by-one clients simultaneously, the aggregate throughput now is going to be about 151 megabits per second because we have a loss due to contention. And also, we're assuming that these clients are not sitting right near the access point. Some of them are going to be 10 feet away. Some will be 20 feet, 40, 50 feet away from the access point. So we're also going to get some loss due to signal strength degradation and rate adaptation. Multi-user MIMO is not factored in. This is for wave one. But we have, by the way, I should talk about how these numbers were derived. They were derived from actually years of competitive performance testing, starting with 11G, right, legacy, and then moving into 11N, and then also 11AC, wave one 11AC. So you determine this by having a group of clients. You start out with one client, you do a throughput test, then you do the same type of client, 5 of the same types of clients, and you do a throughput test, and you look at the aggregate throughput. Then you go to 10, and 20, and 30, and 40s, and 50s, and 60. And what you see is as you scale up the number of clients, you see the aggregate throughput dropping in a predictable way because of contention loss. And you do this test where the clients are all near the AP, within 10 to 20 feet of the AP. And then you do the test when the clients are spread around like they would be in a real environment with obstruction and so on. And then you can see the loss due to signal strength degradation and rate adaptation, et cetera. And so that's how we came up with these values. Now, as we add more clients, we move up to moderate density, 16 to 30 clients. We see that for that same one-by-one group of clients, now we got an aggregate throughput of 139. So they're sharing that throughput. So each per client throughput is going to be less, obviously, and we have about 8% loss due to contention. We keep the loss due to signal degradation and rate adaptation constant at 20. Operating it out neg 80 or neg 70, 5 or something like that. All right. Now here we see we have the number of clients up to 45 clients, so high density, and now we have an aggregate throughput of 117. So you can see we're getting diminishing returns here because we're getting greater loss due to contention. And then finally, very high density. Now you're looking at 87. Well, that's not good, obviously, right? So that's a significant loss due to contention. And that's what, it's diminishing return. So some vendors will talk about, supporting up to 500 clients per AP. Yeah, but if even half of those clients are doing anything on a radio, say you got 250 per radio, and you got 125 trying to do something simultaneously, the throughput per client is going to be minuscule. So while saying you support up to 500 clients is probably good for marketing, but realistically, you never want to design a network that way to support that many clients actively doing something at one time, because the throughput would be pathetic. And in fact, some clients would get starved, i.e., they would get no throughput. All right. So in summary, for basically for 11AC and 11N, this change or this loss due to higher rates of density is consistent through 11N and 11AC percentage-wise. And so you get 35. If you low density, you get about 35% of max data rate, and 32, 27, and 20. So it drops pretty significantly. Now for 11AC wave 2, what would be the corresponding loss percentage of data rate? We don't really know. If anybody says they know, well, I'm not sure if I would definitely believe them, because it would take a lot of testing, a lot of clients, obviously, and I'm not sure if anyone's done this type of study yet. But we are in the process of doing exactly that. So in the future, we'll have some numbers. But we expect, really, what we expect to see is a gain, and of course, and to be more efficient. And we really do expect that multi-user MIMO, certainly if you have a high percentage of multi-user MIMO clients, say one-by-one clients that are multi-user MIMO capable, we see that it's going to mitigate the negative effects of contention loss. Because again, with multi-user MIMO, you're going to be talking to up to 4 clients simultaneously. And so we see that as going to definitely reduce the contention, to mitigate the contention loss. So more to come on that. All right, a little bit about the 120. I just want to point out that yes, it's wave 2, and it's a dual radio AP, and it's up to 800 megabits PHY rate. That's the max data rate on the 2.4 gig radio, up 1.7 gigabits on the 5 gig radio. It supports 4x4 MU-MIMO. It's bold because a lot of the earlier APs labeled as Wave 2 did not support up to 4x4. They only supported up to three clients or three spatial streams, multis and MIMO. The spec says you can go up to 4, and this AP goes up to 4. And also, the other bold thing I wanted to point out is that we support 80 plus 80, and that's non-contiguous 80 megahertz channels, and then 160. Now, until the FCC opens up more spectrum, using 160 in a campus environment is going to be probably unlikely. I mean, you may have some edge use cases where you require high throughput, but low density, relatively moderate or low density, where it may make sense, especially if it's an isolated area where you have plenty of spectrum. You may be able to use 160 megahertz. So if you had some kind of a moderate density location, but it was high throughput and it was isolated, why not use 160 megahertz? Of course, you would have to have Wave 2 clients that support 160 megahertz, but there would be no argument against that using there. It supports 2 gig Ethernet ports, link aggregation. So in the event, if you were like for this particular use case where you had 160 megahertz, doing link aggregation may be required because you may oversubscribe a single gig uplink. So, basically bonding those two ports to a switch, uplink switch, may be necessary so that you don't oversubscribe the 1 gig link. And it's fully operational AAT. Also, I believe it's going to have be able to operate on AF power, but I'm trying to determine exactly which features we have to disable if it operated on AF power. Like for instance, the second Ethernet port and the USB would probably be the first two things that would not be fully functional. But I need to dig into that. Okay, now let's move on to some use cases. But before we do that, we're going to talk about a simple methodology to do some channel capacity planning. Again, you could use a Mojo planner or some other type of planning tool to do something like this. But if you ever want to do it manually and understand basically how it works, back of the napkin kind of calculations, this is a simple method to do that. So step one, we're going to take the application bit rate that's the most demanding, or the service level assurance per user, service level assurance. So if it's HD video or 720p video, maybe I want to do a 5 megabits per second SLA, because I want to be able to guarantee support that HD video streaming on that client or any number of clients. And then we're going to take that SLA, or that application bit rate, the most demanding application bit rate, divide that by the channel capacity, which we're going to refer back to the tables that we went through to determine the channel capacity. It depends on, of course, how many spatial streams the clients have. It depends on how many clients there are, right? Contention loss and all. And then we multiply that times 100 to get the per device airtime. We take that per device airtime now, and step two, and multiply it times the number of devices. And that'll give us our total airtime required, or the total channels / radios required. I say channels because they have to be unique. Because if it's a use case, right, it's going to be in an area, basically for a particular area. And unless it's a very large use case, right, where we can start to reuse channels, so we're talking 30,000 square feet for a particular use case where, APs will not, at one end of the area will not hear the other AP on the same channel because of, basically path loss and so on. Then you would be able to reuse channels, but in most use cases, you will not be able to reuse channels. So they have to be unique, channels. All right. Now, so here we have the requirements and the environment. So it's going to be 125 devices active concurrently. We want to support maybe the lecture hall seats, it's a large lecture hall, maybe it seats 200, but we've done the analysis and we see that maybe 125 devices can be active concurrently. Worst case scenario. So we want to design for that. And we have 11N tablets. Again, this is like for a deployment that's been there for a while. We're not going to actually do, a deployment based on 11N technology. And we want to support a 3 meg SLA, right? So that's per device. So we want to be able to say for sure, when all 125 devices are active concurrently, all of them will be able to support a 3 meg SLA. That's downstream from the access point. DFS channels are available, and no channel reuse possible. It's a small enough space where if every AP can hear every other AP. All right, so here's step one. So we have tablets. There are 11N tablets. We say 125 devices. We know it's going to be moderate because we're going to need a lot of APs. So we're going to spread these devices across a lot of APs, as we'll see how the math works out. 3 meg SLA. Now we have a 48 megabits per a channel. 48 meg. How do we get that? Well, we take the 1x1 client down here, right, and a 40 megahertz channel. It's phi rate. We'll say it's a 150 megabits with short guard interval, right? And we're going to get 32% of that, so approximately 48 megabits of aggregate throughput that we're working with. And so then we're going to take that channel capacity for that given set of clients and the given channel width, and it's up to 40 megahertz for 11N. And then we just determine the per device airtime. 3 megabits by the 48 times 100 gives us 6.25%. That means each client is going to consume approximately 6.25% of the airtime. So then in step two, we have to multiply that per device airtime times the number of devices to give us a total airtime required. And that comes out to 781. That's a very large number for a use case. That means that if we round up, right? And by the way, all of this is only designing around 5 gigahertz. And I know a number of you are saying, well, what about 2.4? And for sure, we're going to have some capacity in 2.4, especially with 11N. The ratio of 5 gig and 2.4, it's not like with 11AC where the ratio of 11AC is like 8 to 1 compared to like the 2.4 gig available if you look at spectrum capacity, and it's going to go up to like 12 to 1 when the FCC opens up that more spectrum that's been identified. But in 2.4, you're certainly going to get some capacity out of 2.4. But just as a matter of practice, I always try to design around 5 gig, knowing that some clients will be balanced or will end up on 2.4, and you'll get some capacity out of that. So there's a big buffer in this particular design. There is a significant buffer available on the 2.4, but maybe you want to use some of that 2.4 for the teacher, for the projection, and put a separate SSID for the projector on one of the 2.4 gig radios. So maybe that takes up channel 1 or something, and you still have 6 to 11 to work with in that environment. But anyways, this is a really extreme example. And would you do this? Would you actually put 8 APs in a small, a medium-sized lecture hall? Probably not. More than likely, what you do is you reduce the SLA. Instead of having a 3 meg SLA, you might have gone with a 1 meg SLA for this deployment. And that may surprise a lot of people that 11N would have trouble doing a 3 meg SLA to 125 clients in a given area. And it's pretty shocking to a lot of people, but that's what you're working with. And again, this is based on actual testing, not based on theoretical numbers, and competitive testing. So competitive testing of all of the enterprise class best performing access points available on the market. And so it's a little bit of an eye opener with how 11N would struggle with this type of deployment. Let's move on to Wave 1. Wave 1, same number of devices, but now we have 11AC tablets. Wave 1 tablets, same SLA, same environment. Same. So this time we're working with obviously more in the way of channel capacity, and we're using 80 megahertz. And make no mistake about it, that's where you get the biggest bang for your buck, is by doubling the channel width. So for those people saying that they want to stick with a 40 megahertz, well, fine, stick with 40 megahertz. You're going to need a lot more APs. So here we double the channel width, right? And when we do that, we also have, let's take a look. We had a 433 megabit phi rate for those 1x1 11AC clients. And we get, now we have a high density because we're going to have more AP clients per radio. And so we use 20% of the max phi, or 117. We do the math. We come out with, taking the SLA divided by the channel capacity and working out the percentage. So now we're talking about 2.56% of the, per device of airtime. Moving on to step 2, we do the math, and now it comes out to 321. That would be the total number of devices times the per device airtime, 321, round up, 4 APs for lecture hall, for instance, the C120. And so we see right away we're doing it with half the number of APs. So that's one reason why you want to go to 11 AC. You do it with half the number of APs. Again, we had to use 80 megahertz to do that. If we try to do it with 40 megahertz, we would have maybe one fewer, because there'd be some potentially, there'd be perhaps it would come out to maybe one fewer AP. But the big bang for your buck is by doubling the channel width. And if you have DFS channels, no problem. If you have most DFS channels, no problem in the US. All right, now we'll move on to wave 2, the last solution. So same number of devices, but now we have wave 2 clients. Of course, these wave 2 clients support multi-user MIMO, same SLA, same environment. Now, we see that we're going to take the same 117, right, that we had before, because we're still using 80 megahertz channels and we're still with high density per radio, but we're seeing a 50% boost in performance from the 117 to 176. This is a actually not really an aggressive number. We've seen results of up to almost 100%, right? So a 50% gain, and if we're using 1 by 1 clients, that means the AP is going to be able to talk to 4 clients simultaneously, as opposed to talking to 1 at a time. So seeing a 50% boost in performance over the 117 is a reasonable, and it's not very aggressive. So with that, we again work out the percentage, the 3 megabits by 176 times 100, 1.7% of airtime, and then we do the math. Step 2, number of devices, and that comes out to 213. So if we take the 213%, round up, and we're going to get some use out of the 2.4, like with previous, and we probably would get a better percentage of boost, and we said 50%. But if we actually have a lot of 1 by 1 clients, or all 1 by 1 clients, this is it's almost close to 200. So it could be even 2 APs, but we'll say conservatively 3 APs. So the wave 2 solution, you saved us on an AP, and that's significant, especially if you have a lot of lecture halls, or you have to do classrooms, and you end up doing 1 AP per classroom instead of 2 APs per classroom, and so on, or rather 1 AP for every other classroom, and so on, rather than 1 AP per classroom. So you can see that the benefits are real in terms of going with the latest technology, if you design the network properly. Again, 80 megahertz, very important. Now, I didn't use 160 megahertz. If you use 160 megahertz, obviously that would make the wave 2 APs even be able to scale much higher. But until there's more spectrum, we would not recommend you use 160 megahertz in this lecture hall use case, particularly since the density is high density. All right, takeaways. So wireless LAN should be designed for capacity, right? We're not designing for coverage anymore. Everyone knows that. And we want to recommend that you design based on 5 gigahertz capacity. Sure, there's 2.4, but if you take for 11 AC, I'll say it again. If you look at the channels 1, 6, 11, that's 3 20 megahertz channels and 2.4 that you have to work with. And if you look at the 5 gigahertz, you have 6 non-overlapping 80 megahertz. So the ratio there comes out to be about 8-to-1. That's 5 gigahertz to 2.4. Going forward, when the FCC opens up that what was identified in pink in that graphic I showed you, then it's going to come out to about 12-to-1. 12 channels to 1 channel for 2.4. So factoring in 2.4 becomes less and less helpful. Let's say it's there, you're going to get something out of it, but really we're designing for 5 gigahertz. Lecture hall, wireless LAN, they very often, of course, they're going to need to support high client density and high aggregate throughput. So you want to make sure that you factor that in. 11 AC wave 2 APs are here, obviously, and people probably already knew that, but a lot of people aren't aware of how many 11 AC wave 2 clients are available. And so I listed some. By the way, that list is just a partial list. The clients that are available is much, much larger than that list that are wave 2. The Mojo Networks is C120 is a true Wave 2. I say that because it supports up to 4 spatial streams in MU-MIMO. Most competitors do not. They support 3, and it supports 160 megahertz. And again, right now you're probably not going to use 160 megahertz in too many campus use cases, but you want to future-proof your network, right? So you want to select it. I would recommend selecting an AP that can support 160. And multi-MIMO will likely mitigate much of the contention loss in high density environments. I mean, it's probably one of the greatest benefits of multi-MIMO, again, is to mitigate that, really disastrous contention loss that we looked at in high density environments and very high density environments as well. You want to opt for a Wave 2 solution that, opting for a Wave 2 solution, it can substantially lower your TCO. You probably, who knows, maybe it's reducing it by 20%, 30%. Now, again, you're going to need Wave 2 clients to really get the most bang for your buck there. So that's something to factor in as well. So that is pretty much it for my presentation, but I do have some questions, so I'm going to open them up. And yes, all right, first question. What do you recommend for the 2.4 gigahertz radios with 11N and 11AC, with the 11N and 11AC Wave 1 lecture hall solutions? Yeah, so in those 2 solutions, remember we had the first 11N, we had 8 APs in the lecture hall, right? You don't have 8 2.4 gigahertz channels to work with. So for the 11N solution, you're just going to want to turn off 5 of the radios in 2.4, basically. So you just have one 2.4 radio on channel 1, one 2.4 radio on channel 6, and one on 11. The rest of them would be turned off because you don't want to have 2 APs in the same area on channel 1. It's not going to help at all. The only time you'd ever want to do that, to be clear, is if you have a bunch of 2.4 gig only clients and you just need them to connect. Realizing that 2 APs would interfere with one another that are on 2.4, but you just need, and that doesn't happen too often anymore because most clients are dual band. Let's see. For the 11AC Wave 1 solution, where you had 4 APs, you basically want to just disable one of the 2.4 gig radios, so you have the 3, the 1, 6, and 11 covered in the lecture hall. For the Wave 2 solution, I should add, then you only had 3 APs. So, you'd have 1, 6, 11 on the one radio on each of the APs, and then the other 80 megahertz channels on the other 5 gigahertz radios. So no need to disable any radios with the Wave 2 solution. With 11N clients, will 11N clients benefit from 11AC APs? Yeah, they will. And the way that they benefit is basically the 11AC APs have just gotten better and better radios in general. Better, more CPU, better antennas. We've improved, over time. We've gotten better at improving, antenna technology. So when we've done comparisons, testing 11N clients with 11N APs versus the same 11N clients with 11AC APs, we have seen an improved performance for the 11N clients when they're connected to the 11AC APs. How much? It depends, 20%, 30, 40% boost. And 40 is a lot. I would say more like, 10 to 20% boost in performance. Is there a good use case for higher end 160? Yeah, well, I'll say potentially, but again, it would be a moderate to low density use case where it's an isolated area where you have plenty of spectrum. You don't have to worry about co-channel interference. And then potentially, maybe backhaul, mesh backhaul or something like that. And again, remember, the way that 11AC works is that it's not an all or nothing proposition for 160 megahertz or even for 80 megahertz transmission. Basically, it has our APs support dynamic channel width. So before the transmission is made, the AP has to determine if the entire 160 megahertz is available or the entire 80 megahertz is available. And if it is, it will use that entire channel to do for the transmission. But if only a subset of channels are available, say the primary channel and then the channel above it or below it for 40 megahertz, the AP will just use 40 megahertz. It's not like it will back off completely until the whole channel is available. So I think people are maybe a little bit, just too worried about using wider channels because they may think it's an all or nothing proposition. It's not. It's not at all. That's not the way the protocol, is spec'd out, and not the way our APs work. So, okay, will Wave 1 client support multis and MIMO with software update? Not according to the vendors that I spoke to, the chip vendors. According to the chip vendors that I spoke to, Wave 1 clients will not support multis and MIMO. They're going to need to be Wave 2 clients. And the slide that I put up there for showing that the Wave 2 clients, those clients actually have Wave 2 chips with multis and MIMO support. Does the C120 support link? Yeah, it does support link ag, but having to use that it's very unlikely that you're going to need it. Again, maybe if you're doing 160 megahertz in those rare use cases, then you want to think about running two cables to a C120. Can you determine if your client supports multis and MIMO? Yeah. So basically, you just do a sniff. You sniff the client as it's associating to an access point, and in the ASOC request association request, you look at the down in the capabilities, VHT I think it is. Very high throughput capabilities. There's and basically it'll say whether or not it's a multi-user MIMO beam or capable, client capable, and also a beamform E capable, because you have multi-user MIMO relies on the transmit beamforming, so those have to be you'll see a 1, which is a yes, and that means it's capable of multi-user MIMO. So you look for that, and also I've seen it in probe requests. So you look at probe requests, or you look at ASOC requests, association requests, and over-the-air capture, and you can see if your client supports it. Let's see. All right, and we probably have some more questions if there are any more. Let's see. I'm gonna have to.
One more I see in there, Robert.
Yeah. Right. Is it best to allow 11AC to be unrestricted in regards to bandwidth throttling, since they can use less airtime and receive quicker data? Right. So, good question. And so the design that I just went through, the process that I went through, there's no restricting of anyone, right? You're trying to make sure you have enough capacity for every application. However, there are going to be applications that you would want to probably throttle peer-to-peer stuff, or stuff that it's not really related to the curriculum, and maybe it could be really high throughput. So you may want to do some restricting if you have some applications that are consuming too much airtime. Then you probably want to try to restrict some of those. You could also do a per client restriction, so that no one can take more than 10 megabits per second or something like that, or even 5 megabits per second. So you could do that per client and as well. So no matter what application they use, because maybe they're using one application today that's sucking up a lot of bandwidth, and it's not related to the actual curriculum, or it's something that not critical. You can restrict that, but then some new applications come along, and you didn't have a restriction for that. So if you do it based on per user, you can catch all whatever application they might want to start using in the future. All right, let's see. Any other questions? If you have any, you can submit them now.
Yep, I don't see any coming in, so I'll just give it another minute or two. If you want to just pull up the next slide, Robert. While we allow any more questions to come through, just wanted to review your free access point today. So for all those attendees to qualify, you get a free access point. We have some qualification requirements that are posted on our webinar registration page, but it is limited to anyone who is a new company. If you've already received a free access point before, you're not eligible. And of course, all of our valued resellers and partners, they are not eligible for access points at this time. But if you have any questions, you can feel free to call us at 877-930-6394, or you can send us an email to the domain you see here, myrep@mojonetworks.com, with any questions you have, and one of our reps will be reaching out to confirm your shipment address and qualification. Again, we thank all of you for your time. I don't see any more questions coming in, but Robert did post his contact information. So if there is anything that comes up at a later time, you can feel free to let us know.
Yeah, and I did want to mention a couple of things. Well, we had a whole series on 11AC, which is available, and it goes through basically the fundamentals of 11AC, and there's also one, channel capacity planning, and then optimization, wireless LAN optimization, as well as best deployment best practices and so on. So if you'd like, those are available. You can take a look at those. And also, Erica, we do have those upcoming webinars, right? Around campus deployment best practices and so on,
Yes.
and administration and so on.
Yes, we do. We have a three-part series coming up at the beginning of April, starting that first week of the 5th. We have part one, which is the Essential Campus Network Guide. First part is designing your network. That is the 5th. And then a couple of weeks later, we have part two, which is deployment. And then finally, part three, which falls into May. And that's actually network management. So we're really covering all three. We're dissecting the essentials of campus deployment and campus network guide. And feel free to, I just posted the link to our webinar page, and feel free to visit that and register for any that you're interested in.